Thank you, everybody, for coming to our talk, our multi-year performance journey in Confluent Cloud. My name is Mark Selwyn. I'm in product here at Confluent. And
I'm Sriram. I'm in engineering.
Yep. So just a little bit about us before we jump straight into it. So I have a database background working in storage engines, indexing engines.
I worked in databases in AWS before. Right now I work on the building faster and cheaper Kafka in Confluent.
Yep. And we would be remiss if we did not say that Sriram and I are simply representing the hard work and dedication of a very talented performance engineering team. So none of this would be possible without them. So to kick things off, you may have been seeing throughout the keynote and maybe in some of our recent blogs that we talk a lot about this thing we call Cora, which is it's a disaggregated, complex mesh of disaggregated services that work together that essentially power Confluent Cloud, our cloud offering, that powers over 30,000 clusters now, works across all the major cloud service providers. And this talk is going to be focusing on how we think about performance, how we measure performance, and some of the interesting things we found specific to Kafka, and also specific to all the auxiliary services that we are required to run to operate our service, and the different performance characteristics. So to level set, to start things off, we're going to start high level, and then we're going to zoom in and get pretty low level as we go. So the first thing we want to talk about is the abstractions, which is effectively the user experience goals that we have. And to kick things off, I want to talk a little bit about the complexities that we're trying to abstract, or the complexities that we're trying to solve for. So as we zoom into that architecture diagram a bit further, you'll see here we have all these arrows, and each of these arrows represents a touch point of some sort. And each of these touch points have an associated cost, a performance characteristic, they have a throughput or capacity limit, and it gets pretty complicated pretty quick when you have to think to yourself, okay, well, what instance type am I gonna use to power the dark blue box? Or what's the right storage subsystem? What's the right file system to use? How much I/O do I need? How much storage size do I need? And things get pretty complicated pretty quickly when you start to look at the fact that, well, these things don't necessarily scale proportionally as with your requirements. For example, in AWS, the M6 series, they don't scale cost or throughput proportionally. So you might have a case where, okay, maybe your use case is satisfied by the compute of an M6 large, but you need the throughput of an M6 extra large, for example. And then once you solve that bottleneck, maybe you uncover a different bottleneck. Maybe you need to increase the amount of throughput going to the storage system, or maybe you need to, or maybe the bottleneck moves over to the network layer. So these are the kind of complexities that we're aiming to abstract from our users. And things get even trickier when you think about doing this across the major cloud providers, because each of these cloud providers, on paper, the instances and infrastructure might look the same, but they behave and perform completely different from each other. So, as far as the user experience or the abstractions that we expose to our users, we have three major abstractions at Confluent. There's the logical Kafka cluster. So this is the Kafka cluster that we give you to connect your Kafka applications to. We call that an LKC. And if you're running on one of our provisioned capacity environments, our dedicated environments, then we also give you a unit of capacity we call Kafka, or Confluent Kafka unit, a CKU, which you can scale in pre-provisioned capacity with. And then more recently, we also introduced what we call a cluster load metric. And this gives users the visibility into their environment to see just how utilized their cluster might be with regard to their application, because all applications behave differently. Some might use more of the infrastructure resources and might tax the system a little bit more. So it's a good indication to say, okay, for my workload, this is how much I'm taxing my cluster. It might be a good idea for me to either add capacity or in some cases remove capacity might make sense. So with these abstractions out of the way, let's talk a little bit about how about the challenges that this abstracting this complexity from our users poses. So performance engineering at Confluent, I mean, we've always cared about performance, but having a dedicated performance engineering team is actually a relatively recent thing over the last 2 or so years. And the challenges that we were faced with was, okay, well, how do we think about performance? How do we ensure consistent performance when we're abstracting just about everything from the user while we're managing over 30,000 clusters, while we're constantly adding new features, while having to adapt to just all sorts of workloads, whether there's standard Kafka workloads or some of the wildest things out there. We also have to run all these auxiliary services for monitoring, logging, for doing even things like tenant management and quota allocation. These are all services that consume resources. So how do we ensure performance or ensure consistent performance while running all of these services, while abstracting all of the low-level stuff from our users? That's the challenge that we took on. So let's dive a little bit deeper into how we think about measuring performance. So one of the first things we started off with was trying to figure out how the heck should we think about latency in terms of an SLO, right? Because after all, what doesn't get measured doesn't get improved. And so what are the things that our users care about that we should be looking at in order to make sure that we're providing a good experience? So we were asking ourselves, okay, do we look at latency at the broker level? Do we aggregate at the cluster level? At what frequency do we look at these things? Do users only care about end-to-end latency? What about producer-specific latency, consumer-specific latency? And then just make things a little bit more complicated, we don't always get the 100% view. Like for example, we don't see metrics coming directly from a user's client. Now hopefully KIP 714 will help us and help the community with that problem, but for now we don't have a way to see how an actual user's application is behaving. So with these challenges in mind, we took a first stab at creating our latency SLO. And so we'll talk a little bit about these health checks that we have, but effectively what we did was we put these agents, both on the produce and consume side, that act as a Kafka application. So this gives us the ability to measure the latency from the producer side to the consumer side and see as close as possible to what our users would see. We aggregate the latencies that we see every minute, and then we had a report that showed us the week-over-week aggregated latency, the P99 latency. This was fine, but it wasn't quite good enough. Measuring things on a week-over-week basis actually did not help us capture the anomalies that we would see quite often, actually. And there's a really awesome talk in this room later this afternoon that goes into some of those things that I highly recommend. But it didn't capture everything that we see, the degraded latencies, whether it's we're experiencing degradation on the infrastructure side or on the network side. And we were missing about 100 minutes of degraded latency in our SLO, which is a problem for our users, right? We want to make sure we're ensuring this consistent performance. So to solve that, we added a new SLO, and this SLO does effectively the same thing in that it acts like a user's application, and it probes every single cluster, or it's deployed in every single cluster. But now we're looking at these at a much higher frequency. So the window is now measured in minutes, and this gives us a good way to capture what the latencies in clusters when there is a problem. And this gives us the ability to even better measure how we're doing. So once we established how we're going to be measuring or how we're going to be looking at the latencies, obviously we have to set up the monitoring in place for us to be able to react to these things or be proactive about these things. So I mentioned that we have a health check agent or agents in every Kafka cluster we host. This, again, is a producer and a consumer, so it tries as best as possible to mimic what the user would see. So it goes through the entire life cycle of a message. And then if any of these messages breaches our SLO, it automatically fires an alert, and the engineering team is alerted to dive in. We also do have quite a bit of automation in place. Again, awesome talk later this afternoon on some of that automation, and Sriram will talk about that as well later in this talk. But we have automated processes in place to help us remedy degraded infrastructure events. And then, of course, we do nightly regression testing. We do about 18,000 hours of regression testing per year. Alrighty, so I'm going to hand it off now to Sriram to talk about the actually interesting stuff, the low-level details.
Thank you so much, Mark. So I'll spend the rest of the talk walking through how we optimized for these two latency SLOs that we have defined so far. Before we talk into the optimizations, we kind of have to understand what the workload patterns our customers are using. Confluent Cloud runs around 30,000 plus Kafka clusters, probably the biggest distribution in the world. So we had the unique opportunity to actually go and figure out what the customers are using or what the customers are doing so that we can go and optimize the workloads for those specific workload patterns. So there are a bunch of factors that go into what impacts the latency. Specifically, you can think of partitions, fan out, throughput, clients. These are the major things that you have. We have workloads ranging all across the board from like hundreds of thousands of partitions. The fan out also varies quite a bit. Same with the throughput. We could go up to like 20 gigabytes in throughput. We also have customers who do 10 megabytes of throughput. The additional variables are around connection rate. There's like requests per second. The workloads can be keyed or unkeyed. So all these different workload patterns that we have, right? I mean, to give a simple example, we run a multi-tenant fleet. All our basic and standard clusters run on that. And the typical workload there is you have like hundreds of thousands of partitions, but it's pretty low throughput, right? And another example is if it's a data pipelines workload where you're like pumping data from a database to a data warehouse, you typically have very few number of partitions, very high throughput, but less number of clients. So there's all these variations that you have that you kind of have to work through and encode and effectively look and see how you can optimize. So what we got right in the first attempt was effectively, we went and built distributed tracing inside Kafka. And then we took all these workloads that we were observing in Confluent Cloud and encoded into open messaging benchmark. It's a very expressive benchmark because it kind of gives us all the aggregate latencies end to end. So, and then what we did was after that, we actually went and built a lot of fail-fast dirty POCs. This was kind of an arduous process because at every layer where we found a bottleneck, we kind of have to make a call whether we have to completely rewrite the layer or mask it or effectively make it more efficient. So we had to go through this for every layer of bottlenecks that we found. What we did not get right, which was interesting, was we were initially hyper-focused on just Confluent's version of Kafka because we thought, okay, all the bottlenecks are probably going to be in the Kafka layer, right? But then, as you guys, as Mark pointed out, there's all these services that we have around Kafka, which is responsible for providing this managed, robust, and resilient cloud offering, which had significant impact to the end-to-end latencies that the customers were observing. So we had to go and split our investigation into Kafka-specific, and I would call it like Cora services-specific to kind of minimize the end-to-end latencies that we have. All right, so given the pattern, the methodology that we used, let's dive into the more interesting details on what are these Kafka-specific and Cora-specific optimizations at a very high level. So this is kind of a high-level example for a specific workloads that we were kind of looking at on the latency breakdown, right? As you can see, the replication layer kind of took a lot of the time. It had a huge bottleneck. We'll talk about all of these in more detail, followed by the network storage and request processing. Again, this is specific to the workloads that we were looking at. Your mileage may vary depending on the hardware, the configs, the workloads that you have. But this is what we kind of observed in Confluent Cloud. All right, so let's go into each of these layers to understand what are the typical bottlenecks that we found and what we did specific to that. So replication layer typically had a lot of CPU overhead, a lot of inefficient allocation patterns. This was actually predominantly visible in workloads which had a lot of partitions, all these multi-tenancy workloads that we were looking at. Replication was a big bottleneck there. So we did a bunch of POCs initially to say, okay, probably there are some low-hanging fruits to fix this layer, and we can actually get away with it. But it turned out that that's probably not enough. So we had to go and completely rewrite this layer. So Cora is coming out with a completely rewritten and efficient replication layer that's going to ship in the next few weeks, which actually minimizes the CPU allocations by a lot, CPU usage by a lot, and the allocations. One interesting key observation that we had is Kafka runs in the JVM, and there's all these GC pauses that happen. And these GC pauses take away around like 20 to 40 milliseconds of time. And the interesting thing is when you're actually doing this distributed tracing, the GC pauses could show up anywhere, and you would actually think the bottleneck is in that layer. So that was actually something that we had to weed out to understand is that the GC pause is actually an issue in that specific layer. But rewriting this replication protocol and minimizing the number of allocations actually gave us the opportunity to minimize the GC pauses as well, because we are actually bringing down the allocation rate. So that's an additive effect on the end-to-end latencies that we have. The next thing is network layer. The key observation here is when we ran this open messaging benchmarks, we saw that the end-to-end latency that's observed from the client side is way higher when compared to the broker side latencies that we have. Because as we only have visibility into the brokers because we are running the brokers in the managed cloud, the clients are running in the customer's application. This is actually predominantly visible with less number of clients, and the main reason that we found was Kafka has this ability to have multiple requests per connection in flight, and it's typically set to 5. And what happened was, since Kafka only processes one of these requests at a time in the broker side, all these other requests are either getting buffered on the client side or the network socket, right? So effectively the higher percentiles, the end-to-end latencies that the clients are observing is pretty high when compared to the broker latencies. So the way to get out of this is we actually increased parallelism in Confluent's version of Kafka to make sure that these requests can get processed much more efficiently instead of being buffered at the network layer. The interesting thing is this actually increases CPU consumption on the broker side, but we still went ahead and did it because it actually gives a very good minimization of the end-to-end latency. Well, the next interesting thing is storage. In storage, the interesting thing is you have all these background operations like compaction and like catch-up consumption. These things actually interfere with the real-time foreground operations that we were looking at. So the improvement here was, we've built tier storage. Tier storage has been there in Confluent for quite some time. It's coming to Apache Kafka with KIP 405. It actually provides compute storage separation, which actually helps with elasticity, by the way, specifically. But then the side effect of that is all these catch-up consumption and compaction actually happens from the object storage instead of using the disk throughput. So effectively, we get the disk throughput back for all these real-time foreground operations, one. And we can control the rate at which these happen in the background instead of relying on things like page cache, read ahead, and stuff like that. So that actually helps with minimizing the impact of the storage layer. There's a lot more to do in this layer. There's an impact of the page cache and stuff like that, which we'll probably work on the next few quarters. And I think we should minimize the latency and the impact from these background layers pretty soon. The other thing is the file systems and the page cache parameters actually played a huge role in the latencies as well. So we've kind of heavily tuned those file system and page cache parameters to help with these end-to-end latencies. The final thing for the Kafka-specific optimizations is one of my professors told me, performance is nothing but an infinite number of infinitesimal improvements. There's a lot of low-hanging fruits. If you profile Kafka, you can see that. Typically, the improvements kind of are split into either you minimize the work per request, or you kind of move it out of the critical path, or there are all this GC and kernel parameters tuning. One concrete example I can give is, for example, one of our customers complained about offset commit rate, that their offset commits were pretty slow, and it is also impacting their real-time produce and end-to-end latencies. When we went and observed, what happened was these offset commits were actually being processed by the request handler threads one at a time. And then when the request handler thread processes it, it actually has to go and take the partition lock, the group coordinator lock, and stuff like that, which is actually slowing down the processing of other requests in the queue, but also taking a lot more time to process these offset commit requests. A simple optimization that we did was we actually took all these offset commit requests and put it into a separate queue, which was being processed in the background. And then effectively it will batch off all these offset commit requests and take the lock once and commit them at the same time so that it increases the throughput of the offset commit rate. So this is an example of moving the work out of the critical path, and then so that the request handler thread and the queues become free for other foreground operations that you have. So in this case, the offset commit rate increased by like 3x for this customer specifically. So there are a ton of optimizations across the stack that we have in Kafka, from the consumer fetch to the replication fetch, authorizer, and stuff like that. It's probably a full talk to talk about all of these in specific detail, but that's kind of the high level of all the infinite symbol improvements that we have in Kora. All right, so we talked about all the Kafka-specific optimizations. What about all the Kora services-specific stuff, right? So this kind of a latency breakdown that we found of all the services that we have in Kora that was causing latency impact. I'm not going to go into each of these services because they're very specific to Confluent Cloud and our managed offering. But it's kind of an example. And you can see the monitoring service is kind of the biggest. It takes away a bunch of time from the end-to-end latency. So what did we do here? One observation was some of these services are actually bin packed with Kafka because of the environments that we use. Bin packing is a Kubernetes thing where you have this agent sitting alongside Kafka. And it's actually using the same hardware resources as Kafka was using. So either we actually went and completely re-architected some of them, we enforced QoS by setting the request limits, resource limits, and stuff like that. I mean, one concrete example again here was this monitoring agent I talked about. What it was specifically doing was, it was actually every few seconds it would wake up and it would do a JMX fetch to Kafka. It's responsible for getting all these metrics and submitting it to an observability platform outside. And when it does this, Kafka has to kind of allocate a lot of memory to send and then to serialize this data over the wire and send it to the monitoring agent. The monitoring agent would like remap it, and where it consumes a bunch of CPU, and then it actually sends it over to the observability platform. This whole thing was inefficient. It was built so that we get this feature in place first, but then it was built in a very inefficient way, so it's completely being re-architected right now. One learning from this was we actually did not build with performance as first-class citizens. It was kind of an afterthought. So when you're building a managed service, a learning is to build this as first-class citizens. Otherwise, you kind of have to dig yourself out of it once these features are out the door. All right, so we did all these optimizations. What about the results? What happened at the end of the day? So this is an example of comparison between Confluent Cloud versus Apache Kafka on 2 CKUs, which is where you can go up to 100 megabytes of throughput, and 9,000 partitions with 1:3 fan-out. So you can see that we can, Confluent Cloud's latencies is pretty low, whereas Apache Kafka kind of is linear with the number of partitions that you have. So here in this case, we are up to like 10 times faster when compared to Apache Kafka. Very similarly, if you increase the number of partitions, you can see that Apache Kafka performs very poorly as you increase the number of partitions, whereas Confluent Cloud is way better, up to 10 times better. Again, of course, it should be obvious that it will not be 10 times better in every workload out there, but our commitment is to ensure that we're always better than Apache Kafka on the same hardware, or probably way better on the same hardware in Confluent Cloud. A blog post with all these details is coming out in the next few weeks once the replication optimizations go out. And it will have a lot more details about all the different workload patterns I talked about and how we perform on the same hardware when compared to AK. One other interesting thing here is AK is here running on the same EC2 hardware, the full EC2 hardware, by the way, whereas we have all these other services. Even though we've minimized the impact of it, they're still running bin packed along with Kafka. So it's like fighting with our hands tied behind our back. Anyways, so again, steady state latency is one thing, which is great, but the next thing that affects the end-to-end latency is also the degraded state latency. So Mark kind of gave an introduction of what this is. So the recap is the end-to-end latencies for the degraded state is actually looking at per window, per cluster, because we want to cap these short intermittent spikes that you could have in the latencies that you're observing. Typically, we have seen that this falls under three categories. One of them is either you have a degraded cloud hardware, either have a degraded cloud service, or you have like a workload-induced imbalance, workload-induced degradation, or there are all these multi-cloud vagaries. We'll talk about all of them in more detail now. So degradation in the cloud is real. If you've been running a cloud service, this is something that should be obvious to you. Hardware goes bad, there's a lot of jitter, or the storage has latency spikes here and there. In the last few weeks, what we have observed is running all these 30,000 clusters is a few incidents where there was complete block storage outage. Sometimes the disk got wiped out as well. The other thing is we have had tens of incidents with external connectivity loss and then storage and network degradations. So the improvement that we have here is we have proprietary APIs in Confluent that is able to transfer the leadership to a non-degraded broker, a non-degraded AZ, when these kind of incidents happen, again, without any compromise on durability and availability for consistent performance. I mean, you can have these APIs, but you can't go and trigger them every time it happens, right? It's a lot of on-call overhead, so you have to build automations around it so that you can actually scale sublinearly with the amount of clusters that we have in Confluent Cloud. So we had to build this the automation where we actually monitor the metrics from all these clusters, aggregate those, and then if the latency goes above a specific threshold in the cluster, then it automatically triggers and mitigates the impact of the degraded hardware. Again, it's triggered more than 500 times in the last 30 days, so it happens quite a few frequently. If you want to understand more nuances and implementation details about this one specifically, one of my colleagues is giving a talk in this room at 2:30 in the afternoon. I would encourage you folks to attend it. This is a graph, cute graph. It sees like one of the customers actually had these latency that's spiking up to the moon, and then like after 5 minutes, the mitigation kicks in and effectively makes sure that the latency comes back to earth. I mean, we are trying to make sure that this actually shifts left. Instead of having 5 minutes, we probably want to make it like in a couple of seconds. The next kind of degradation that we can see is all this workload cost imbalance. Workloads keep changing all the time, and that causes an imbalance in partition distribution. It also degrades the latencies. So Cora comes with this component. It's a service called self-balancing cluster, which continuously rebalances the cluster. We've been having this for quite some time. But the rebalancing initially was very slow, and it was very heavyweight because it used to compute all these optimizations up front and go and apply the rebalancing at one shot. So this layer has been completely re-architected now to be more real-time so that it is very fast with respect to any of these imbalances that happen in the cluster, and can go and change the partition distribution very, very quickly. So this is one of the examples of a customer who actually saw this 25% reduction in their load once we released this into the fleet. You can see that the health check latency end-to-end came down from like 60 to like 10 milliseconds for this customer. The interesting thing to call about any of this is that customers didn't have to do anything. Effectively, they just woke up and they're like, oh, my latency is great, my broker load is good, because these optimizations are continuous. It keeps happening in the background because we are working on it and taking care of your clusters in the cloud. The other thing which is very interesting is all these multi-cloud vagaries. We all know that AWS and Azure and GCP, they all have different instance types. But one interesting thing is the same instance type could have different hardware configurations. Like you could come up with like a Broadwell or a Haswell CPU or Ice Lake or Skylake. You have to read all this fine print to understand what's the CPU that it's using, what's the clock speed of it, etc. If you have different clock speeds, each broker will behave very differently in terms of latencies. The other thing is the throughput and IOPS are also not scaled linearly between different storage classes. For example, GP2's throughput and IOPS scale very differently than GP3. GP3 has a lot more baseline IOPS when compared to throughput. So we have to be very cognizant of all these items, the cloud vagaries, before you can actually deploy your solution. Some cloud providers don't even have throughput and IOPS scaling independently. Like you have to only increase the disk size for you to get better throughput or IOPS. So the improvement I will call about here is I'll go back to what Mark talked about in the first slide, which is about abstractions, right? We have a contract with the customers saying that this is kind of the throughput that you're going to get with the amount of CKUs that you have. So behind the scenes, we can actually go and continuously make these optimizations behind the scenes, so that as new hardware comes out, we can make them available to the customers without them having to even worry about anything. Also, we tune a throughput and IOPS very, very significantly. When we moved from GP2 to GP3, we changed all our page cache settings to make use of the better IOPS in GP3 so that it gives a better price to performance. The second thing is we've moved to Graviton in all of Confluent Cloud. So we have more than 20,000 instances running in AWS Graviton. It's, for people who don't know, Graviton is the ARM processor. It's not the Intel processor. It gives much better price to performance in AWS. We also consistently switch between memory and compute instances in other cloud providers as well. So this is one example. I think Julie talked about this in the keynote. The example where a customer actually filed a support ticket asking us, okay, why did their end-to-end latency actually go down? Like what happened? Like, is there any issue with the cluster? Turns out that some of these optimizations that we have been building actually rolled out seamlessly to this customer. And what instead happened was we passed on some of these performance optimizations as cost optimizations to the customer because they were able to downsize their cluster because it is the amount of broker load actually came down very, very significantly. All right, so what are the learnings through this multi-year journey? This is our learnings. A couple of them are the primitives vary very widely across cloud providers. It's a complex distribution. So we believe abstractions are required to provide a unified multi-cloud experience across all the different clouds that we have. The second thing should be obvious. You cannot improve what you cannot observe. Also, the measurements have to take care of the outliers. It's not just, you cannot have relaxed measurements. The third thing is we have to build with performance as a first-class citizen across the stack. It's a feature. It's not like an afterthought. The steady-state latency optimizations, aka benchmarks, are necessary. It's a guiding light, but it's not sufficient because there are a lot of other things that happen when you put things in the cloud. The last one is cloud hardware or services degradation is real. It's actually very, very frequent. So resiliency kind of needs to be built in when you are providing a managed cloud offering. That's pretty much our talk. Thank you so much for attending. We can take any questions if you have.